Hello, everyone, and welcome. This is Melissa Miller, Director of Executive Operations with the Office of National Security at Texas Tech University. Thank you for joining us for our second session hosted by the Critical Infrastructure Security Institute. This series is designed to bring together partners across academia, industry, and government as we work to strengthen collaboration and advance shared priorities in national security and critical infrastructure. We're grateful you're here and we look forward to today's discussion. Before we get started, just a couple of quick housekeeping rules. As you have questions that come to mind, please place them in the Q&A as we should have time for discussion at the end of today's presentation. Also, there will be a small survey and it will be very helpful if everyone would complete it. Before we begin today's session, I'd like to take a minute to share a brief overview of our institute. The Critical Infrastructure Security Institute was established in August of 2024 in response to growing national security needs. Our university president, Dr. Lawrence Skubanek, recognized the urgency of this effort and made a significant investment to launch the institute. On the screen, you'll see the full range of CISA critical infrastructure sectors currently being addressed across Texas Tech. And within the Institute, our primary areas of focus are telecommunication, defense, and energy, with a growing conversation in agriculture and water. In April of 2025, House Bill 5092 introduced significant changes to the Reese Technology Center in partnership with Texas Tech University. Today, this former U.S. Air Force base, located just 10 miles from TTU's main campus, is known as the Reese National Security Complex. One of its major advantages is the private airfield, which includes 2 active runways and is designated as a federal restrictive airspace, which is also known as a FRIA. As many of you are aware, the Critical Infrastructure Security Institute broke ground on the Critical Infrastructure Security site here at Reese National Security Complex on May 19th, 2026. It is my pleasure to introduce our guest speaker today, Dr. Argenis Bilbao. He is an expert in power systems and artificial intelligence applications for energy infrastructure. His research advances the reliability, effectiveness, and intellectual of modern power grids through innovation in microgrids, machine learning, and power electronics. With that, please join me in welcoming Dr. Argenis Bilbao.
Thank you very much, Melissa, for that great introduction. Um, today, thank you all for coming, by the way. And today I'm going to be talking about microgrids. I'm going to be giving a brief introduction on microgrids and their role in this data center age that we're living in. So first, I have a little slide about myself. So I'm going to talk about my educational background. I am an electrical engineer by formal education, got a PhD at Texas Tech University, and I have a very, very strong computer engineering IT background, as that's what I worked in the industry in those fields in the past before I became an electrical engineer. Some of my research interests include power systems, cybersecurity, microgrids, and microgrid controls, more importantly, not just microgrids, but the controls. And I have a lot of interest in conventional and renewable energy power generation, as well as what Melissa mentioned, artificial intelligence and machine learning. I cannot claim I am an AI/ML expert. I am merely a user, but I apply those tools in the energy field. Power electronics, I love them. They're all around us. We need it. And power semiconductor devices, which are, of course, components within power electronic systems. Now I'm going to transition and let's start talking a little bit about the subject matter now. Let's talk about microgrids and energy sources. So before we begin, I guess to get started, let's say, well, what is a microgrid? A microgrid is a localized electrical power system that integrates energy sources and loads. So generally, these energy sources are distributed, geographically distributed, which is actually a great thing in the case of microgrids. These all are defined within a boundary. And microgrids can operate either connected to the main utility or they can operate independently of the utility, which brings a lot of advantages that I'm going to be discussing in the next few slides. In the next few slides, when microgrids operate independently from the utility, that is, it is said that the microgrid is operating in an islanded mode. Some of the sources typically found in microgrids are, of course, solar photovoltaic energy sources, wind turbines. We also have conventional power generation like natural gas generators, perhaps diesel generators, and other more exotic sources and power generation system like CHP systems. This stands for combined heat and power and fuel cells. So that's just a few examples. Of course, there could be other sources like nuclear energy sources in microgrids, which it's great in my opinion. So some of the advantages about the using the microgrid models is that, well, and I'm not, just because of time, I'm only going to be mentioning the two main ones, which is number one is increase the power system resiliency. And by that, I mean that they can operate in island mode during natural disasters, for example. So let's say that there's a downed line somewhere as a result of let's say, a tornado, a hurricane. The microgrid can isolate itself and operate in islanded mode, preventing or minimizing the downtime. So as a result of this, of course, microgrids can recover quickly from such events, and it reduces, and this is a very important one, because microgrids use distributed energy resources, meaning resources that are geographically distributed. They reduce the dependence on long distance transmission. Okay. This is something that is very expensive. So transmitting power from the source of the generation to the consumers is very expensive. And we're looking at about $6 million per mile for power transmission. This is an exorbitant value. It reduces this because, well, all the loads are co-located with the energy generation, which means that you don't have to transmit it, and it's a great thing. The second advantage is, well, it increases the power system reliability by providing continuous power during those outages. It reduces the frequency and duration of those outages and service interruptions, and it maintains electricity supply for critical facilities like data centers. Yes, I'm mentioning data centers, but of course, things like hospitals are critical loads. Definitely don't want a power outage in the middle of a surgery, for example. That would be absolutely disastrous, as well as power outages in airports. It's definitely not a good thing. It also enables automatic fault isolation and restoration, and this is all done at the control level on the microgrid. So Texas happens to be a natural fit for microgrids, primarily because Texas leads the growth. I mean, it's the undisputed king when it comes to the growth of renewable energy. So, as you probably know, Texas has a large amount of wind generation and it has a growing amount of solar generation. So, here are some of the numbers here. Texas leads it for sure. We have more than most every other state. And so, for example, in terms of wind energy, Texas has a up to 23% of the state's total generation in wind. And in terms of solar, Texas has up to 12% of penetration. So these are not small numbers. I mean, these are very significant. In addition to generation, Texas also has a very, very good amount of battery energy storage capacity. We have a total of 4.3 gigawatts of energy storage, which is great, not only for renewables, but also for conventional generation. It's a good thing to actually store energy whenever it's very cheap to produce and perhaps release it at a time when generating that energy is not as economical to produce. So, in terms of solar energy, it's expected to grow by 41 gigawatts over the next 5 years, which is it's an incredible pace. So, for those of you that may be familiar with the power and energy field, you probably understand this terminology. So 40 to 50% of the energy, Texas has on average from 40 to 50% renewable energy penetration, which is not shabby by any means. It's actually fantastic. And in isolated cases, the renewable energy penetration can reach up to 70%. This means that at any particular point in time, 70% of the Texas energy comes from renewable energy sources. Okay. And again, this is the peak. It doesn't happen that often. Most of the times it's 40 to 50%. But it has happened where we have reached up to 70%. So just to put some numbers, I mean, what does it actually cost? I went on a little bit of a research streak to find numbers published in scientific literature and by independent surveyors of what does it cost to generate electricity using different sources. So, and this is important to lead the conversation coming up on data centers. So it turns out that the undisputed king of, I guess, cost when it comes to energy production is utility scale PV generation. And you can see in this table over here, 38 to $78 per megawatt hours is the cost for solar, which is very good. Then this is followed by onshore wind. So it's the wind energy that is produced inland, followed by natural gas, which is the lowest cost dispatchable energy source produced by fossil fuels. Then followed by geothermal. Geothermal, yes, it works, but unfortunately, it's very geographically limited. Not you don't get that energy in many states. It's almost like hydroelectric. For example, we don't get hydroelectric here, but it is definitely a very reliable source of energy. Then there is coal, then offshore wind, which is pretty expensive. It's right now it's really hard to justify a offshore energy offshore wind energy power plant because of the expense. Then there is a natural plant, peaker plants. For those of you not familiar with what that means, the natural gas peaker plants actually produce power only in the event of a very high demand of energy. So these plants are generally off and they're not producing anything, but they're so expensive because they are not very thermally efficient. So it takes time to actually spool them up, heat them up, get them to operating condition to supply a peak demand, and that makes it very expensive. There's also some standby costs associated with it that makes this type of plant very expensive. And unfortunately, the most expensive type is actually nuclear. Um, I have to say about nuclear that it is my personal opinion that nuclear is what will take us to the next level. We definitely have a lot of need for energy, not just in Texas, but throughout the United States. And I think that nuclear is what will be able to give us that energy to provide that base load. With that said, it is the most expensive one. However, it provides the most reliable source of that base load energy. Uh, it is unfortunately so expensive, primarily due to regulations and, well, the dangers associated with it. But once the plant is running, if you ignore those things, it's actually very economical and very reliable. So we're actually trying to work towards making it more economical. And you may have heard about the micronuclear reactors. That's one way that we're looking at reducing the cost of nuclear energy. So, anyways, what I'm trying to say here is given everything that I have discussed, microgrids are natural companions for data centers. You can have all this distributed generation, wind, solar, nuclear, diesel, natural gas far away from urban cities and have a data center located right at that location and not have to transmit that power. So yes, it's a natural companion for data centers. Now, talking about microgrids, I want to take a few minutes to talk about the Gleam microgrid. So I am, in addition to being a professor at the Electrical and Computer Engineering Department, I am a assistant professor to be exact. I am the senior director for the Gleam project. And what the Gleam project is, it's a project that seeks to bring together researchers from multiple disciplines to perform research under the energy umbrella. And in order to do that, we have developed a microgrid here at Texas Tech it's actually located in the Reserve Force Base, and I will show a map a little later about this. So some of the research areas we do with this microgrid, of course, as you probably know, there is a lot of cybersecurity involved when it comes to data centers, and not just data centers, just in the grid as a whole. Just about everything connected to the utility and every piece of apparatus is now connected to some sort of a network so that it can be remotely controlled and data can be accessed remotely. So cybersecurity, we look at smart grids, we look at solar and wind generation, of course, conventional integration of conventional energy source integration into the grid are things we actually look at, and controllers, AI, ML, those in greens are the some of the areas I actually have funding for including power semiconductor devices. So in terms of assets, these are some of the assets that our microgrid has. And we are under normal conditions connected to the utility through a 1 megawatt transformer. And however, we have conventional generation like diesel. We have a half a megawatt of diesel generation, and that we actually have two generators. We also have renewable generation, like our solar power plant that is good for 350 kilowatts. We also have electrical loads that can be resistive or reactive, so that we can tailor experiments uh, for whatever use case scenario we have in mind. In addition to that, we have battery energy storage, which, as I mentioned before, is great for renewables, but also for conventional energy generation. And we have a number of software licenses for simulation. Uh, I would say, as many universities have, this is not super unique. So things like MATLAB, COMSOL, Silvaco, HyperSim, Voltron, we have licenses for all of that, which really helps when it comes to simulation of grid-related things. So this is just a quick picture of all those assets. So it's not, I just figured I'm not just going to tell you about it, but actually show you guys some of the assets. And you can see here we have the one of the diesel generators in the upper left. And I don't know if you can see my mouse, but here it is. We have solar over here. We have our load, our control building, which now houses a data center. And it's an NSF data center. I'll talk more about that in the next few slides. And we have battery energy storage. This is just one of the cabinets we have. We have an additional one that is approved. So it's approximately 500 megawatts of megawatt hours of energy storage. And yes, this is all here for research. So if there's anybody in the audience that is looking forward to performing research and needs a site to perform that, I would be happy to hear about what you're trying to do. Perhaps we can get something done together. So another diesel generator here. This over here in the middle, this E-gauge system box is actually used to monitor the power consumption and generation for the entire site. And I will talk a little bit more about that coming up. But we have electrolyzers, batteries, inverters, hardware in the loop simulators, you name it. This is all for research purposes. This is what the control building looks like on the inside. And we can see that we have a number of industry standard equipment for protection, like breakers for everything that's connected onto this into the bus of the microgrid. We have four quadrant inverters, the automatic transfer switch, and a utility input cabinet and associated protections for it. Um, Let me draw your attention on this bottom picture over here. So if you can see towards the right, this is how we started doing research on data centers with just some decommissioned old equipment. So we had 3 racks decommissioned from the High Performance Computing Center, and we were looking at the energy impacts associated with those computers. And that was probably about 5 years ago now. And now I mean, this building looks completely different, and you'll see that in just a bit. So inside of the control building, as you can see, we have monitors to be able to, well, monitor everything that's happening within the site. So all the metrics, all the heartbeat, if you will, we can monitor that. And this was all done by our students. So we're very proud of them. And some of the older ones, they have moved on and they're working in key parts of the utility sector companies. For those of you familiar with electrical connections, I decided to put this over here. This is what the microgrid looks like electrically. So, of course, this is a simplified electrical diagram, but you can see this line right here in the middle. This is the main bus of the microgrid. So this is where everything gets connected to. So we have our solar plant generator generation. We have an old power plant here, 200 kilowatts connected to the bus. We also have 150 kilowatts connected to the load. And even our neighbors actually decided to work with us and Sandia National Labs, and we have a connection between the two facilities so that they can send us wind power if the experiment requires it. So this is a fairly complete site. In addition to this, we have our loads. We also have this, which is what feeds the data center. So energy comes from the bus, goes into a UPS, and then it feeds the data center that we have in there. Of course, being a UPS, it can support the data center if there's a power outage or perhaps a glitch in the power of any sort using its internal battery. So this battery can support it for 5 minutes at 200 kilowatts. So, and this is what the beautiful site looks like. What I like to show about this one is that we have a ton of space out there, and any work anybody would like to do with us, we have the space for it. So in the past, we have had work where the Army has actually brought some of their generators to us for analysis on some issues they were experiencing with nonlinear loads. And of course, well, we had no shortage of space to accommodate them. So physically speaking, I don't know if everybody in the call is from Lubbock, but we are actually located in an Air Force base, a decommissioned Air Force base called it was called the Reese Air Force Base. It is now called the Reese Technologies Complex, and this is where we're physically located. So it looks like it's in the middle of nowhere. I don't like to think about it this way because it's only a 20-minute drive from the main Texas Tech campus. It is a fantastic drive. So now let's go a little bit into data centers. So for those not familiar with the term, I decided to put this in here. So a data center is pretty much a facility that houses computers and networking equipment primarily. And it's used to store, process, and deliver digital information. So think of it as uh, just a home for a lot of these computers and cloud services. Okay, so pretty much, I mean, to put it into plain English, when you open a website, when you watch a movie online, when you store pictures in the cloud, send emails, or maybe use ChatGPT, that's actually going through a data center. So even when you take up your phone and put those happy faces for your favorite posts, that's all going through a data center, okay? So in terms of what we care about this is, well, how much they consume. I'm going to just tell you the extremes just for the sake of time. So pretty much a small enterprise server, I guess, data center. When it comes to just the computer side, the computers, the networking equipment, they can take anywhere from 50 to 500 kilowatts of power. And if you put in all the HVAC systems that are required, the lighting for the facility, things like humidity control equipment and so forth, this number can go up to 75 kilowatts to 750 kilowatts. So for those of you not very familiar with what these kilowatts are, pretty much that equates to 250 houses, average houses worth of electricity. That's how much. And this is a small data center. Okay. Just keep that in mind. On the other side of the spectrum, we have the big ones, AI, HPC data centers. So we're talking about Google, Facebook. Well, it's not Facebook anymore, it's Meta. I can't get I can't get that straight anymore. I always think Facebook for some reason. But anyways, those are actually consuming anywhere from 100 to over um, 500 megawatts. That's not a trivial amount of power. And once again, if you factor in all the lighting for the facility, humidity control required, lighting and everything else, all in, we're looking at 150 to 700 plus megawatts. And in terms of how many houses that equates to, that's 233,000 houses worth of power. That is a lot of power. So, so anyways, that's where we're at right now. So we are expected to grow threefold by 2030, okay, when it comes to the data center power consumption. So right now we're sitting at approximately 292 terawatt hours per month worth of electricity usage. But in 2030, we will be looking at, or this is the expectation at least, but I think we're pretty well on our way there to 600 terawatt hours per month of electricity. This is not a small amount, and that's why the alarms are sounding. So, that's not the only problem. Sure, the volume of electricity being consumed, yes, it's a big problem. I mean, we don't know where all that electricity is going to come from, but that's that's not the only problem. Another big, huge problem that nobody's really talking about is how dirty the power can get in the presence of data centers. So pretty much data centers they are seen by the grid as a nonlinear load because they all have power electronic converters inside that create nonlinear current draws, which means that you end up with very bad displacement and distortion power factors associated with them. And what this means is that, well, you have very high THD or total harmonic distortion in the current waveforms. And in plain English, what does that mean? It means that, well, the power transformers on top of the poles, they don't, they suffer. They physically suffer and wear out as a result of this. The insulation gets essentially damaged. They heat up. They damage the oil. And, well, overall, the effect is damaging of those components. The transmission lines themselves actually suffer because they're not being utilized efficiently as a result of the reactive power that is consumed by those devices. Of course, because of this, the losses in the electrical system as a whole increase, which means that if you're transmitting, let's say, 1 gigawatt on one end, the receiving end of that power is only going to be receiving, let's say, um, 90 gigawatts. So it's a 10% loss. And I'm just uh, communicating my idea of efficiency power distribution. And one last thing that I'm going to be mentioning is that they unbalance the three-phase power system. The three-phase power system is I guess, industry standard way of transmitting electricity by using only three wires. But then when it's unbalanced, that means that there is more power flowing through one of the three lines, or maybe two of the three lines, than the other lines. And this actually creates a physical problem with the turbines that generate electricity, regardless of what fuel type they use. So this creates a lot of problems, and Down here, we can see this is actually from my data center. This is data that I got from our instrumentation. And for those of you that know your power electronics, you can see that we have very high harmonics going. So this is phase A, B, and C. Going in phase C over here, we have approximately 50% total harmonic distortion, which means that the harmonic waveforms are 50% as large as the fundamental itself, which is 60 hertz. So this is significant. This really tears up the electrical power system. So now I'm going to go on to have a brief discussion about the data center that I have at the Gleam microgrid site. So this is the REPAX project, and this acronym stands for Remotely Managed Power Aware Computing System and Services. Okay. So I'm not going to delve too much in this, but these are some of the projects we have at Gleam, and the NSF Repax is actually a $12 million project by the NSF, and that's what allowed us to bring this data center here to Texas Tech University. We have approximately here, counting off the top of my head, approximately 20 people working on this project simultaneously to try to solve some of the problems that arise as a result of data centers. So pretty much the main focus of the REPAX project is to see how we can modulate the power consumption of the data center so that instead of becoming a burden to the grid, it becomes an asset in stabilizing the utility grid. So, and there's a number of ways we do that, which I'm going to discuss in the next, I think in the next 3 slides or so. But anyways, that is the main goal. And here are some other goals as well, or focus areas. So some of the focus is the improvements to data center infrastructure control. Once again, energy is oftentimes generated far away from urban areas where people don't actually live at or have to travel long distances to go and push a button. So the idea is that we really want to improve the way we remotely manage those sites. You would think that, for those that haven't been into a data center, that this is all highly automated and everything works almost like a sci-fi type of thing, but in reality, no. There is a lot of human interaction involving keeping these computers up and running all the time. So we're looking at ways of really, really minimizing that so we can more economically put those data centers out in the middle of nowhere where the generation is at so that we don't have to transmit that power to the city because it's expensive. So we're looking also at the ability to adjust workloads to match data center load conditions, including the availability and cost of electrical power. So again, if you can modulate the power consumption of the data center, if for whatever reason, let's say there's a very high peak demand in the summer because, well, it's too hot. Well, if we can throttle the data center down, it would really help stabilize the grid instead of having to, well, just turn on those peaker natural gas plants, which are very expensive. And I mean, a lot of you are probably not strangers to that, where if you remember the Uri storm back in 2021, some people had at their regular homes power bills in the $10,000 range because the electricity was just so expensive. And it's because, well, we had to power up those plants, and well, the cost of electricity skyrocketed as a result. Excuse me. So just some specifications of the little cluster we have here. I have to say this is a little cluster, um, even though it is representative of what's actually out there. We have a total of 110 computer nodes, so just 110 computers in this cluster. And that comes up to about 28,000 processors in this cluster. It's an AMD cluster. Unfortunately, Intel, it's a little bit behind right now. I'm an Intel guy though, but hopefully we'll get back up soon. In terms of GPU resources, we have 8 nodes with each one of them with four H100, so Hopper architecture GPUs for doing AI ML type of work. In addition to that, of course, every data center needs some amount of storage, and we have a total of 2.5 petabytes of storage. And while that sounds like a lot for a home computer, it's definitely almost nothing for a data center. But once again, this is a small model data center that allows us to do all sorts of testing and well, development of technology that we will hopefully transition out into the real world once the project is done. So in terms of power consumption, this data center can actually consume, at least from datasheet type of values, up to 380 kilowatts, where 200 kilowatts are for the computers and networking equipment themselves, and 180 are for the cooling. Okay. So talking about that, I'm going to show some pictures of what that power draw looks like for this specific cluster. So this is just a picture of the front of what it looks like. This cluster is actually housed in this control building for the microgrid, and it has its very own enclosure that has the air cooling for cooling the entire cluster. Then all that heat goes outside to a set of condensers, and this is a completely waterless cooling system for the data center. So it doesn't consume any water. There are data centers that actually do use water, and but well, that's another subject. I'm not going to be speaking much about that. But anyways, in terms of the power consumption, this is what the cluster power consumption looks like. So generally speaking, this particular data center or computer cluster draws about 75 kilowatts of power. And I don't know if you can see my mouse. Actually, I don't think you can, unfortunately. But let me see if I can make it show. Laser pointer, yes, there we go. It shows. So anyways, you can see that this is approximately the baseline power consumption for this tiny data center, about 75 kilowatts. However, when the data center is loaded, you can see that there are spikes that go up here all the way up to 110 kilowatts. And I have seen significantly higher power numbers than this. I have seen it go up all the way up to the rated 200 kilowatts. But because this project is relatively new, we do not have that many users just yet. So I expect these numbers to go up significantly. But anyways, the bottom line is that as the power center is used, the power usage actually peaks, as you can see over here. Unsurprisingly, this is the power consumption of only the cooling portion of the data center. So it's hovering at about 20 kilowatts, as you can see here, but there is a very strong correlation between the data center usage and the spikes in the cooling. So I'm going to switch back and forth between these two so you can see it. So you can see how when the data center usage goes up, so does the power usage of the cooling. So this is something I like to say all the time. We we are paying for the electricity to heat up the room, but then we're paying for the electricity to cool it back down. And that looks almost like it makes no sense, but that's what we're doing. But anyways, with the exception of this peak and this other peak over here, you can see that it tracks very well. Okay. So that's somewhat unsurprising. But this here, it doesn't track perfectly well because, well, there are times when, well, the temperature is just very hot and the cooling system just has to work harder on those days. So our solution to the problem is, so pretty much if you're going to be modulating power and working with power, there has to be a power awareness. So for that reason, we install a lot of sensors throughout the facility to be able to monitor those. So we have current transformer installation at all the energy sources, all the loads, which of course include the data center, overall data center, and at the node level. So at each individual computer, we have a power monitor to be able to see what that computer is drawing. So in addition to that, as you guys just saw, we do have monitors for the data center cooling, and we have monitors for the lighting, humidity control systems, and whatever else is in there, cell phone chargers, whatever, it's all monitored. In addition to that, as you know, temperature is a very a very big thing when it comes to data centers. And we have sensors, temperature measurement sensors inside of the data center and outside for doing things like predictions. So for data center load modulation, which is the big thing here, we are looking on the software side of things for CPU frequency scaling. So the lower the frequency, the less power the data center actually draws. And we're doing the same with GPUs or graphical processing units. We're also controlling the node's power state, and this is done by communicating directly with the computer BIOS. We are also controlling node power consumption by manipulating the BMC or the baseboard management computer, which allows us to completely turn off a node. That really saves a lot of power because then the memory is not connected, it's not drawing power, and so forth. So we also have AI/ML models that we are developing, and some of them are made already for characterizing the energy consumption of the individual jobs that are running or that will run on the data center. So that way we can more intelligently schedule the jobs to run at times where it would be perhaps cheaper to run that job. Okay. And one thing that it's a little bit of my brainchild is let's say energy market for job scheduling. So think about the ERCOT market, but for data center jobs. That's something I would love to actually implement in this pilot study. And we're not there yet, but it's something that will hopefully come in soon. So anyways, that's the end of my presentation, and I hope you all enjoyed it. Thank you very much.
Dr. Bilbao, we actually have a couple of questions.
Mhm.
The first one is regarding the SMR information that you mentioned earlier. One of our guests has asked if TTU will be pursuing small modular reactors to help power RNSC projects.
Yes. Well, I don't understand the question, but yes, I mean, I am a 100% for SMRs because, well, they're great for providing that baseline load. And I guess if the question is how can we collaborate? Yes, I'm pretty sure that Melissa will be sharing some information about me, some contact information. So I would love to hear all about it because I honestly think that is the future for providing that baseline load. So thank
Okay.
you so much for that comment. Really appreciate it.
Yeah, so for the individual that did share that out, we are starting to work on our master plan for our overall site. So, as Dr. Bilbao stated, I will be sharing some contact information at the end. So, please feel free to reach out. We're definitely looking for energy partners that we would be involved with small modular reactor research.
Awesome. That's great.
Um, and another one that we have is directed towards you, Dr. Bilbao. So, looking ahead 5 years out. How do you see the capabilities evolving and influencing national security, specifically grid resilience?
That's a really great question. That it is because yes, there is going to be a very big influence. So so all this consumption definitely, and all this energy has to come from somewhere. And right now, the utility, the power infrastructure is not ready for it. It's unfortunately not ready. I mean, I'm painting a gloomy picture, but that's where we're at right now. And unless we start investing in not only creating new infrastructure, but also updating, upgrading, and maintaining the old infrastructure, we're just not going to be able to get there. I mean, and if we get there, it's going to come at a cost of national security because, well, we're going to have more common power outages. And this is something we cannot afford to have. It's just something that I think I have in my presentation, but I failed to mention, is that military bases, all of them have a microgrid of some sort, just to be able to increase the resiliency and not have any operational losses. So yes, to answer the question, absolutely, there is going to be a big impact if we don't do something about it. Yes, we all want to have happy faces on Facebook, but I mean, that comes at a cost, and we have to
Yes, sir.
upgrade everything.
Yes, sir. Another question is, again, specified directly to you. Can you share a little bit as to how you work with industry partners in your role as the director of Gleam?
Okay. Yes, we have a number, for the industry, you only have one real method. And yes, I am part of the university, but I have developed with the contracting office a contract template that allows external partners to use some of the assets that we have here, some or all of the assets that we have here at a fee. So these fees primarily just for maintenance cost. And of course, there are things like insurance requirements. Let's say that for whatever reason, the experiment that you want to run breaks something, uh, there has to be a way for us to recover the cost of the equipment. Normally, we haven't had any issues. We haven't had to have any sort of insurance claim, but that's the way. So we have set contracting methods to make that happen, as well as set scheduled fees to allow outside partners to collaborate with us.
Yes, sir. Well, Dr. Bilbao, those are all the questions that I have received so far. I want to check the Q&A. Oh, I think one more just popped in.
Mhm.
Let's see. Are the center's CPUs, GPUs, and NSF cluster resources hardened against EMP?
Oh, that's a really good one. Unfortunately, I would say the only EMP protection this particular cluster has is just the fact that it's inside of a metal building that is grounded. That would provide it some protection, but of course, it is not protected against conducted EMI that could potentially be transmitted through the input wires into the building. So this one is not. However, if for whatever reason you're interested in doing EMP attacks, we have, well, it's not part of Gleam. It's CC is actually, well, CC actually has something going on to address such type of research. So I'm not going to speak much more about that because some of that is somewhat sensitive, but I'll leave it at that. Yes, we're thinking about that. However, the current data center uh, is not specially hardened for EMP.
Yes, sir. So, Dr. Bibla, I think those are all of our questions. If you'll move the slide forward one for me. I would first and foremost like to thank you for your time today and all sharing out all the information about protecting the infrastructure through energy systems, your expertise, and for helping us better understand the role energy systems play in strengthening and supporting our national security efforts. And if you'll transition one more time for me. So this is the conclusion of our Lunch and Learn. Thanks to everyone who joined today's session. We do hope that you have found the discussion informative and valuable. As part of our ongoing Lunch and Learn series, we're pleased to share that our next session will take place in October and will feature Mr. Aaron Tyner, and he'll be presenting on cyber vulnerability mitigation in cyber physical systems. We hope you'll join us again, and we appreciate your continued engagement with the SISI community. For more information about the Critical Infrastructure Security Institute, please visit us at, and it's located at the bottom of the slide, but it's depts.ttu.edu/CISI/, and our email address is listed down there as well. So if you have any questions, comments, or concerns, please feel free to reach out through email and we will get a follow-up to you. You're able to sign up for our newsletter there as well. We hope that you have a wonderful day. And again, there should be a small survey that comes at the conclusion of our session. We hope that you have a great Tuesday and look forward to seeing you again in October. Thank you for your time.